Okay, the recording has started. So good morning, everybody, and welcome back to Math 115. So today I was going to sort of continue on with this right triangle trigonometry stuff and do some more examples. But I changed my mind because I graded the exams yesterday, and I'm basically almost done grading them. I just have a couple last things to finish up. And then I plan on posting your grades basically after class today, or after office hours today, that is. So I'll post your grades, and then those of you who submitted the exam in the correct PDF format, I'll send you an email with your exam with handwritten feedback on it. So the exam went about as I had expected. The class average for this exam did take a dip. It took a bit of a dip, but I was sort of expecting that, and that's sort of typical for this class, just because this exam was. I mean, the material that's on exam 3 is harder. So the average was somewhere around 71%. So our previous exam averages were, I think, like 78 and 79 respectively. Exam 2, and then, why is this happening? What is this? Stop it. Okay, you don't need to know what the other exam averages were. They were 78 and 79, I think. So this exam seems like people found the material from this unit to be harder than usual. And I want you guys to succeed on the final. So I figured what I would do today is go through the exam and give a detailed solution to some of these problems, because some students seemed quite confused by some of these problems. So if you have your exam handy, it might be useful for you to take a look at your exam while you're watching this lecture and see what kind of mistakes you made and how you could maybe correct those mistakes. Okay, so that's what I'm going to do for today. So before we start, are there any questions, or is anybody in opposition to proceeding with this exam for class today? Okay, seems like not. If I finish early, then I'll go back and do some notes. Okay, so we'll just kind of start off, and maybe I'll get you guys involved a little bit with these. Okay, so the first one, question, pretty standard stuff. This was mainly about angles, okay, and their measurement. Okay, so we had instructions for how to convert an angle measurement from radians to degrees. Okay, so we want to go from something like 2 pi radians to 360 degrees. Okay, or something like pi radians to 180 degrees, right? And what we want to know is, well, what are the instructions on how to convert? Okay, what are the instructions on how to convert? So you could put it in a number of ways, but most students who answered this problem correctly gave the so-called cheat code of just multiply by 180 over pi. Okay, so we take 2 pi and multiply by 180 over pi, we get 360. If we take pi and multiply by 180 over pi, we get just 180, right? And so on and so forth. So this is the way we can convert between radians and degrees. Or you could think about it, if you really wanted to get really technical with it, you could say, well, x radians over 2 pi is a percentage of a full revolution, then apply this percentage to 360 degrees, which is a full revolution in degrees. Okay, so that's a pretty standard problem there. Okay, and then we're asked next, okay, to give 3 different angles, alpha, beta, and theta, which are coterminal to the angle pi over 6. Okay, to the angle pi over 6. So this next problem sort of requires us to know, well, what is the definition of angles being coterminal? And we said that theta and theta prime are coterminal if theta prime equals theta plus 2 pi n, where n is an integer. And I'm going to use this notation that we learned in the last class and just put in z, because z was the thing where the symbol that we had for the set of integers. Okay, so negative numbers and 0 and positive numbers, but no fractions or decimals. Okay, so an integer. Okay, so if we want to find alpha, beta, and theta, which are all coterminal to the angle pi over 6, well, we can just take, I suppose I could just take the first one to be pi over 6. And then I'm just going to add 2 pi n. So beta could be something like pi over 6 plus 2 pi, which would be like, I don't know, 13 pi over 6. And then alpha could be, I don't know, we want to find one which is coterminal to these guys, but different from the 2 that I already have. So I'll add 4 pi this time instead. So I'll take my n, the integer n, to be not 1, but 2. And I'll get pi over 6 plus 2 pi times 2. And that'll get me 25 pi over 6. Okay, so what does this look like on the unit circle? On the unit circle, we're talking about angles which are coterminal. So our initial angle here is pi over 6, right? So it looks something like this. So this is pi over 6. And our next one looks like, oh, that doesn't show up very well. Our next one looks like go all the way around and then some. So that's 13 pi over 6. And it ends up facing in the same direction, right? And we can also have one that goes around twice and then ends up in the same spot, and that would be 25 pi over 6. Okay. So that's how we would find 3 different angles, alpha, beta, and theta, which are coterminal to the angle pi over 6. For B, would it be okay if you wrote them out as degrees instead of radians? Absolutely. Perfectly fine if you write these as degrees. So this one would be 30 degrees, or this one would be 390 degrees. And then plus 360 would get us 750 degrees. Yeah, perfectly fine. If you want to express your angles using degrees or radians, they're the same thing. Now, what would not be good is if you said, well, if you said something like theta is equal to 30 degrees and beta is equal to pi over 6, then you'd be in trouble because you haven't answered the question correctly, because theta and beta are the same angle. Okay, and we were asked for different angles. So that would be a one pitfall that you could fall into. So we want to make sure we're giving different angles. Okay. So this next one, okay, asks us something about, what's the deal with coterminal angles, right? Okay, we get it. We know when angles are coterminal, but what is the, what's the point? Who cares if angles are coterminal? What is the, what can we know if these angles are coterminal? And I kind of gave you a hint. I said that there is going to be some relationship holding between the values of sine theta and sine theta prime. So let me ask you guys, what do we think it is? If we have two angles, theta and theta prime, which are coterminal, what do we think is going to happen to the values of sine theta and sine theta prime? At least got two questions right. Yeah, sorry, I meant to return these exams to you before, but hopefully you guys have your exam nearby and you can check. Okay, so what's going to happen to the values of sine theta and sine theta prime? So yeah, I mean, we're going to have probably one of our angles would be like a reference angle, which would be between like 0 and 360. And then the other one, of course, if we want it to be coterminal, we're going to need to add plus or minus 2 pi. So that will probably push us out of that interval for the second one. But I'm asking something about the values of the trigonometric function sine theta if or sine theta and sine theta prime if theta prime and theta are basically some interval of 2 pi apart from one another. Right. So Savannah's correct. Yes, Heidi and Savannah both got basically the right idea. Okay. If we look at what the definition of the sine is, it's the y value of the point on the unit circle which the angle points at. So this point right here, x comma y, well, if our original angle is theta and then we have a coterminal angle, it points in the same direction. So these two angles point at the same point on the unit circle. And so their sine of theta is equal to y here. And that's also equal to sine of theta prime. So that's a unit circle way of seeing it. But you could also see it in terms of, well, if theta and theta prime are coterminal, then theta prime is equal to theta plus 2 pi n. So the question is, what's the difference between sine theta and sine of theta prime, but I'm going to replace theta prime by theta plus 2 pi n. And now you should be able to tell me what relationship holds between these two things if I write it like this, because sine theta is a periodic function with period 2 pi, right? The period of the sine function is 2 pi. So this should be an equality here. Yeah, so coterminal angles point at the same point on the unit circle, and this was sort of the whole point of why we care about coterminal angles, is because if we can say that two angles are coterminal, then we can say that their the values of the trigonometric expressions will be the same. And this was how we kind of tied in the idea of reference angles. If we want to compute something like sine of 750 degrees, well, I can use this theory, which I just kind of wrote down, along with the problem in the previous problem. Well, instead of doing sine of 750, I can just do sine of 30. These two will be equal because sine is a 2 pi periodic function, right? Or these two angles are coterminal. So rather than memorizing and learning how we do trigonometry for every single degree measurement up to like a billion or negative a billion, we just take our degree measurement and we subtract 360 until we get something which the angle is between 0 and 360, and then we do that instead. And we know that'll be equal, and we sort of have a good idea of what the sine of all of these angles are. Whereas 750 degrees is really hard to visualize. If we do the difference, then we will get negative value, right? Let's see. Difference. Do you mean sine of theta minus 2 pi n? Is that what you're talking about? Could you clarify your question? Okay, yeah, so minus 2 pi n is still equal, okay? So here's how you can see why. If I have the unit circle, if I subtract 2 pi from this angle, oops. If I subtract 2 pi from this angle, let's see what happens. If I take this angle and subtract 2 pi, then it's like I go around in the clockwise direction by 2 pi. Okay, so here is theta minus 2 pi n. Okay, it looks like this. If we measure it from our original point, from our original axis, it looks like this. So this is the angle theta minus 2 pi n. So subtracting 2 pi n, we still get a coterminal angle. It's like, if I start, if this is a top-down view of my head and I start facing in this direction and I do a 360 in this way, or if I do a 360 this way, I'm still going to be facing the same direction. So it will still be equal. Because also remember that n is an integer. So n could be, for example, a negative number. So we could do sine of theta plus 2 pi times negative 1. And that would be the same thing as subtracting 2 pi. Okay, so that's still going to be equal. Okay. I want to make sure I can get through the whole exam, so I'm going to move a little faster now. Are the angles theta and theta prime equals pi and 355 pi coterminal? Well, we need to check, is theta prime equals 355 pi equal to theta plus 2 pi n, which is equal to pi plus 2 pi n for some n. So we need to ask ourselves, can I add a multiple of 2 pi to pi to get 355 pi? The answer is yes. Pi plus 344 pi is equal to 355 pi. And this would be pi plus 177 times 2 pi. So in this case, n is equal to 177. So if we start facing directly to the left, and then we do 177 full revolutions, then we'll wind up facing to the left again. This is how this works. Okay. So next question was true and false. To catch up on time, I'm going to try to go through these ones fairly quickly. We'll come back if there's questions on these. So first of all, 1 over secant x is equal to cosine x. This one's true because secant x is equal to 1 over cosine x. So 1 over cosine x is equal to 1 times cosine x over 1, which is equal to cosine x. And this was 1 over secant. So this one's true. It's a reciprocal identity. Okay, the next question is cosecant x is equal to 0. And the easiest way to see that this does not have a solution is to write 1 over sine x is equal to 0. And imagine, okay, for this to be true, we would need, we're taking a positive number and dividing it by some other number. There's no way to divide something by a number, a positive number by another number, and get 0, right? Sine is between -1 and 1. Sine of x is between 1 and -1. Okay, so the smallest number that 1 over sine could be would be something like 1 over -1 would be like -1. Okay, and then as the value of sine increases from -1 to 0, this number is going to be getting more negative. Okay, so sine of x in this denominator here, there's no way to divide 1 by another number and get 0. This can't be done. Okay, also you can look at the graph of cosecant if you want. It looks something like this, right? The graph of cosecant looks something like this, and so you can see that it doesn't touch the x-axis anywhere. Okay, it just kind of floats above and beneath. So this one's false. Okay, the next question is f of x equals tangent of x is a 2 pi periodic function. This one's false. It's a pi periodic function. Okay, remember we had a, s, t, c. So in this case, we had that in either of these two regions, which are just 180 degrees apart, we're going to get those same values, okay, right? Because negative y over negative x is the same as y over x. That's basically the reason. Yeah. Okay, so that's the next one. Okay, then the unit circle has radius 2 pi. This is a false. The radius of the unit circle is 1. This is why we call it the unit circle. It has circumference 2 pi. Okay, and then finally, this one was maybe the trickiest true and false question. The statement says, well, if x is between 0 and 1, then sine inverse of x will be between negative pi over 2 and 0. And here's how you can visualize it. Remember, if we're working with sine inverse, we only care about the right half of the unit circle. So let me just draw a unit circle, and I'll highlight the right half for us. So we're only interested in the right half. And what is x between 0 and 1 be? X is the input of the sine inverse function. The input of the sine inverse function is a y value of a point on the unit circle. So x being between 0 and 1, this is telling us that our point here has the form something comma x, where x is a positive number. Okay, so this condition, 0 is less than x is less than 1, tells us that our y value has to be somewhere positive. Okay, which means that our point is somewhere on the top half of this, or the top quarter of this unit circle. And sine inverse returns the angle theta such that sine of theta gives us that value. And all of the angles theta which are in this quadrant have measurements which are between 0 and pi over 2. So sine inverse of x is hence going to be less than or equal to pi over 2 and larger than or equal to 0. Actually, strictly larger and strictly less than. Okay, so this was the sine inverse function x, or sine inverse x function. You could also have tried, just do sine inverse of a half. 1/2 is a number which is between 0 and 1. And if you do this, you get opposite leg is a half, pi over 6, or 30 degrees. So we found out that this wasn't true just from this one counterexample. It would also work. Okay, so those are the true and false. And this is the question that I really wanted to get to, because this was the one that gave the most people trouble. Okay. And I think that a lot of wait a second. No, yeah. This is fine. Is this fine? Wait. Yeah, this is fine, right? Let's remove it to the right. Yes, this is fine. Okay. Sorry. I got tripped up for a second. Okay, so I think a lot of students maybe got intimidated by this problem because of this thing inside here looks kind of gross. And it just seems like so hopeless when we have such a complicated function inside of a word problem. But what I'd like to hopefully show you guys is that this problem is not that bad after all. Okay, it's not that bad after all. After all, this function is just a transformation of a sine function. Okay, the transformations are 20 units up, right? 10 unit vertical stretch, pi over 26 means horizontal stretch by 26 over pi. And finally, a shift, horizontal shift, 14 units to the right. Okay, if you want to do these in the correct order, this one should be at the top. Horizontal shift, 14 units right. And then I think we should do the 20 units up should be last. Sorry, I'm not being a very good instructor right now. Okay, this is how we should do it. Okay, so this is what this function is. Okay, and what do we want? We're supposed to find the x value, which will cause the y to be 25,000 bananas. Of course, y is the number of bananas in thousands. So what do we want? We want y is equal to 25. Find x. So we can set up our equation. 25 is equal to 20 plus 10 sine of pi over 26 minus 14. And we can rearrange this a little bit by subtracting 20 from both sides and dividing by 10. And we would get 1/2 is equal to sine of pi over 26 minus 14. Okay, so we have a sine function. And then we have an input. Oh, sorry, this should be an x here. We have a sine function, and then we have an input, and then the output is 1/2. Okay, we have a sine function with an input, and the output is 1/2. Okay. Now we know that there's lots of y values of the sine function which are going to reach this 1/2 value. So we should also note in the problem that we're supposed to find the xth week of during the first year. Okay, this during the first year is telling me that x should be less than or equal to 52. Okay, so we want to find solutions to this equation such that x is also less than 52. Okay, so from here, students took a couple of roots. The not as good route is as follows. The not as good route was to then apply the sine inverse function. And this was then equal to pi over 26 x minus 14. And then sine inverse of 1/2, that gets us like pi over 3. No, sorry, that would be pi over 6. And then this is equal to pi over 26 x minus 14. So then, no, sorry, I wrote this down wrong. X minus 14 is supposed to be in parentheses. I was wondering why that was going like that. So then we get like 26 over 6 is equal to x minus 14. So then we could call this 13 over 3 minus, no, plus 14 is equal to x. So then 14 times 3 is what? 28 plus 14 is 42. 42 plus 13 over 3 would be equal to 55 over 3 is equal to x. And this is something like 18 point, I don't know, what is it? 55 over 3. 18.333 repeating. So then people said, okay, therefore it's in the 19th week. We sell 25,000 bananas at the supermarket. And this is an okay way of doing things. This is an okay way of doing things. But it doesn't get you all the way there. Okay, and what I'm about to explain is why that's the case. Okay, so the reason that this method is not as good is the following. If we consider our original equation, which we're trying to solve, okay, so I just want to take a look at this one underlined in this red highlighter here. This equation, okay, has many solutions, okay? This function here looks like a sine function. So if we were to graph it, it looks, you know, something like this, right? Wiggling all over the place. And then 1/2 is somewhere here, and we just check, well, where are all the solutions of 1/2 is equal to this sine function? And the problem with applying the sine inverse function is that you will only find the solutions which are between like a very small window, okay? And we don't necessarily know yet how long the window of 1 year is. And it turns out that the window of 1 year goes from here to like over here, and there will be more than one solution. Okay, so the sine inverse function really exists in order to, it exists because we limit our frame of reference. And if we limit our frame of reference, then we're not able to answer this question in the most complete way. Okay, so the most complete way to answer this question would be to think about the unit circle. And if we consider the unit circle, and we want to know, well, when is sine of x going to be, when is sine of some angle here going to be equal to 1/2? Well, we want to know when does the unit, what angles produce a point on the unit circle which intersects the line y equals 1/2. So here's y equals 1/2. And we get 2 points. We get this point over here and this point over here. Okay, and sine inverse will only focus on the right half of the unit circle, which is fine when you're trying to use sine inverse for the sine inverse purposes, but it is not going to give you the most complete answer to this problem. Okay, so we've got the following. We have pi over 6, and then also the angle 5 pi over 6. So sine of pi over 26 times x minus 14 will be equal to 1/2 whenever the input of this function, pi over 26 times x minus 14, is equal to pi over 6 plus 2 pi n, or pi over 26 times x minus 14 is equal to 5 pi over 6 plus 2 pi n. Okay, and now what we should do at this point is solve each of these equations individually for x. Okay, so I should add a page here. Whoa, Notability just crashed. Hope I didn't lose all my work. Okay, good. We're getting this straight up. Okay, so let's solve these two equations. The first one is, oh man, I did lose some of my work. So the other one was pi over 26 times x minus 14 is some multiple or some coterminal angle to 5 pi over 6. Okay, so I solve each of these for x. The first one gives me, let's see, we multiply by 26 over 2 pi, we get x minus 14 is equal to 26 over 6 plus 2n, 52n. Is that right? Yeah, 52n. And then the other one and finishing up, we just get x is equal to, well, 26 over 6 is like 13 over 3 plus 14 plus 52n. And then the other equation gives us x is equal to, let's see, 5 pi over 6. 5 pi over 6, when we multiply by 26 over pi, we get 5 times 26 would be what? It would be 125 plus 5 is like 130. 5 times 26 is 130, right? Yeah, I think so. So then we would divide that by 6, and then we would add 14, and then we would add 52n. Okay, and what we need to do now is consider all the values of n which we can plug into either of these equations and get something which satisfies the criterion x is less than or equal to 52. Okay, and well, we can see that this first equation, really the only thing that we're going to be able to plug in for n here and get something meaningful is going to be 0, right? Because if we add 52 to a positive number, then x is going to be larger than 52, right? So this one gives only n equals 0 is the only one which satisfies the x less than or equal to 52 case. So we get our previous one, which was like 55/3. And for this one, well, let's see, this number here is something like, I don't know, what is 130? 130 divided by 6 plus 14. This is something like x is equal to 35.66 repeating plus 52n, right? And well, if we add 52 to 35, we'll get a number which is larger than 52. So again, we find that n equals 0 is the only one that makes sense. So it turns out that x equals 35.66 is also a solution. Okay, so there's 2 weeks in the first year where 25,000 bananas are sold. Okay, and now I will explain this using the graph of this function. Okay, so this is a function which is 52 periodic, okay, because the period gets stretched by 26 over pi. So what does this function actually look like? It looks like a sine function. Okay, so I'm going to draw the graph of sine pi over 26 x minus 14. I'm going to draw the graph of this thing. It's 52 periodic. So here's 52. Okay, that's the 52nd week. Well, the sine function starts by basically going up and then coming down and then going back into here, right? This is how the sine function usually looks, except we've got this horizontal shift to the right. So what are we going to do? We're going to take this whole thing and move it to the right 14 units. So this is our new starting point at 14, and probably sine comes down like this a little bit. And then we go all the way to 52 plus 14. This is what our function looks like. And we're trying to find the points on this graph which intersect the line y equals 1/2. And it turns out that this happens in 2 places. It happens when x is equal to 18.33, and it also happens when x is equal to 35.66. Okay. Okay, so this is, this is definitely the most challenging problem on the whole exam, and I was quite pleased for the most part if you were able to make it to 18.33. And I think if you went beyond that, I was thrilled. Okay, so any questions about this third problem on the exam here? Multiple kind of ways that we can think about it. But the issue really with the sine inverse method is it's only going to show you the solutions up to this first peak here. Okay, so this is why it only tells you sine inverse is only going to give you the information which answers this problem, which lies within the confines of this box. And that's not the confines of the box which is given in the word problem, which is a slightly larger box. Actually, it goes from here to here. So this is what the issue with using the sine inverse function for this problem. Okay, so I guess a word of advice for the exam is for the final exam. If you see something complicated like this, don't immediately freak out. Just remember that this is nothing but a transformation of a sine function. And we know lots and lots of things about trigonometric functions, and so we can try to make use of all of these things. So first of all, we can make use of the periodicity. So lots of people wrote down that the original period of sine is 2 pi, and if we stretch it by 26 over pi, then the period of our new function will be 52. So it's a 52 periodic function, okay? Which, if we want to consider what's happening in the first year, we need to understand what is happening in the first period, okay? Which is why I drew this red box, which describes exactly the first period of this function, going from 0 to 52, okay? And it turns out that every value of the sine function will be taken twice in the first period of the function. Okay, well, not everyone. Everyone except for this one up at the tippy top. It's the one exception. But most values will be taken twice in this region. Okay, so that's why we have to be a little bit clever about the way we solve this problem. Okay. So, any further questions or comments on this problem? Did you hate this problem? Spent a lot of time on this one. Yeah, I was amazed actually. Some students were really, were very persistent with this problem. I think there were one or two students who literally plugged in every single value of x, which was between 0 and 52. And that was really impressive to me. It works. I mean, you can find the weeks. It's just very tedious to compute this 52 times. Okay, well, I think I'll save the rest of the exam for next time. I should be able to finish 4 and 5 pretty quickly at the start of next time, and then we'll move on to talk about more right triangle trigonometry. Oh my gosh. Yeah, so yeah, this was a hard problem. Okay, so if you struggled with this, you're not alone. Many students in the class struggled with this problem, so it's a hard problem. Okay, we'll talk about the rest of the exam next time, and then we'll do more right triangle trigonometry. So if you have questions, or if you want to study, or if you want to talk over your grade or anything whatsoever, please stick around after class. Office hours start now, and they go for the following 2 hours. So I'll be in here. Yes, I am uploading the grades right after this. As soon as I'm done with office hours, I will upload the grades. Or if there's no students in office hours, then I'll just upload them. Okay, everybody, have a good day. Unless you're sticking around for office hours, in which case, go ahead and type out your chat messages in the chat or speak up on the microphone and we'll talk things over. Yep. Thanks, everybody. You guys too. Yep, you too.
Hey, Mr. Hamry. Can we go over my grade and like what I have now, and then like what I need to make on the final to make a B in the class?
Yeah, sure. So let me stop recording.